All right, let's take a second to talk about how we can use calculus now to to get new power series from old known power series. Before we only used basic algebra, but now let's read this theorem carefully, what this text here is saying, so we can understand what's going on. So we're going to use the known series that we have, the one that's geometric series with ratio x, right? And we're going to take integrals and derivatives, so integration and differentiation of that given series. For that, we need to know which rules to use and when we're allowed to use those derivatives, how the interval of convergence changes over those operations, under those operations. So let's read this theorem carefully, see what's going on. So we're going to begin with a series this way. Let's say it has radius of convergence r. So this is a regular power series, n times x minus a to the power n, when n goes from 0 to infinity. And we're going to say that since this has radius of convergence r, that means that in this interval, a minus r and a plus r, each x value that I choose gives me a certain number for the sum of this series, right? So that's what it means for the series to converge. Each x in that interval makes the series converge to a certain total sum, and that sum I'll call f of x, okay? So we're starting with the power series and defining a function based on that series. That's what the theorem is saying for now, just for starters. Note that it's not saying that the interval of convergence is this. We're not saying that. We're saying that the radius of convergence is r, and the interval of convergence could or could not include the two endpoints, okay? We're saying in the open interval, that happens for sure. Maybe on the closed interval as well. The theorem is not saying anything about that. We have to test it on our own, okay? Each endpoint of the interval at a time. So, right, the theorem is also saying how to derive the function, which works exactly how you would think. You know, if the function is this in yellow in the middle there, if you want to take its derivative, then all you got to do is use the power rule. You see that? There's the power, there's power n, it comes down, comes right here, you see n, and then you subtract 1 from the power to get the n minus 1. That's the only place where x shows up, so you don't need to use product rule or anything. Cn doesn't have any x's in it. So you can take the derivative just as normal. Not all functions have derivatives, right? So that's already a plus that the theorem is giving us, that we're able to take the derivative because the function is differentiable. If we ended up with something that was an absolute value or something, would not be able to take its derivative where the inside of the absolute value equals 0. The function is not differentiable there, but that's not going to happen if we have a function defined this way through a power series, which is pretty cool. And you should also remember from calculus 2 maybe that every differentiable function is continuous. That would be calculus 1 actually, but then in calculus 2 you'd see that a continuous function is integrable, meaning you're able to take the integral, find the integral of that function, and the integral, not surprisingly, works exactly the same way that you would if you just forget about the summation symbol. And look at this, just add 1 to the power, the n becomes an n plus 1, right? And then divide by the new power, sort of reverse power rule. Exactly how you would derive, let's say you have an x to the power 6, you want to take its derivative. That's just 6x to the power 5. Exactly, the 6 being the n comes down, and then the new power is 1 less. And if you want to take the integral of x to the power 6 like this, you add 1 to the power, that's x to the power 7, but then you got to divide by 7 and add a plus c like you see over there. So this theorem is just telling us what we already wanted, we wished happened, which is that we were able to take the derivatives of the terms of the power series normally. So I'm not going to bother with the proof of this theorem too much. It's kind of technical, right? Because it's just confirming intuition. What it does is sort of, you see that this is already a limit, this is already a limit of Sn when n goes to infinity. And then the integral is also, the derivative, excuse me, is already a limit as well. So this is the limit when h goes to 0 of f of x plus h minus f of x over h when h goes to 0. So this is a limit. And then this is a limit also. So this is the limit when n goes to infinity of the Sn, but not just any Sn. It's Sn when you plug in x plus h into x in the power series. So maybe Sn of x plus h minus limit of Sn of x when n goes to infinity. My h's and my n's are kind of looking similar right now, so gotta be careful here. But the point here is that we're just playing with limits, one limit after the other. Everything is fine. So there's no really big idea going on. It's just a limit and another limit. There's a limit of h, a limit of n. At a certain point, you want to split those apart and take two limits at a time, or switch the order and do the limit with h first and then the limit with n later. I'm not gonna, like I said, not gonna go too deep into this proof. I just want to tell you that there is a proof to this theorem. Like every theorem has a proof, and we're gonna just follow the rules that it sets out for us. So let's see some applications and some ideas here. One more thing to be said is that the radius of convergence remains the same. When you take the derivative, you get a new power series, and you take the integral, you get a new power series, but the radius of convergence is the same as the radius of the old one. One thing that could happen is that you might end up with a new interval of convergence. So like I said before, we don't know about whether this is closed or not, or closed on one side or the other. And as you take derivatives and integrals, that could change. So you may lose endpoints or gain endpoints depending on what happens. Let's go ahead and check it out through a few examples at the bottom there. I have a couple that I separate for us to work on. So 3a is asking us to find a power series representation for each of the following functions and to determine its interval of convergence. Again, our starting point is always the known series. Let's work with a first. We always know this as x to the power n and 0 to infinity being, the geometric. So we always know this with interval -1, 1 open for sure, right? So this is the interval of convergence of this one. We don't have to test it again because you already know that when x equals 1, this doesn't converge. When x equals -1, this is just alternating -1, 1, -1, 1, -1, 1. This is not going to converge. So here we know this is the interval of convergence. So maybe I'll take the time to write this down just to be super clear about it. Now, this is known. This is in black is known. What I'll do now, looking at the right-hand side of this and thinking maybe for a few seconds, if you do the same, you want to pause the video, you can think, what can I do with the black function, black series to get to the series that I want here in item A? And if you think derivatives, then you're correct. You can see that the right-hand side of this is 1 minus x to the power -1, like so. Taking derivatives of both sides is going to give you, on the right side, you're going to use power rule, -1, 1 minus x to the power -2, like so. So chain rule plus power rule. And on the left, you just take the derivative through the regular power rule, which is what the theorem told us to do. Yeah. And so the right-hand side becomes exactly what we wanted from item A. And so let me move this a little further down. I thought I wouldn't need that much space. Maybe I got to manage it better for the next one. But we're almost done too. Let me organize a bit better. Let's move this over to the left. Move this over to the left and squeeze things in a bit. Then we can continue to see that this sum is minus 1 over 1 minus x squared, which is not exactly what we want. There's an extra negative that we see over top, that we don't see over at item A there, which is here. So to really finish it up, we have to move this negative over to the other side. So I gotta see that by multiplying, excuse me, then I'll get this. So this will be minus n, moving the negative 1 over, multiplying n, like so. Some people don't like to have the n minus 1 here in the exponent. So what they do is they just sort of shift the counter here for n. So if you think about it for a second, plugging in n equals 0 would give you 0. And then, so that's not going to make a difference. And then plugging in n equals 1 is going to give you x to the power 0, which is 1. So it's going to be minus x to the power 0. And then minus n equals 2 now to x to the power 1 and so on. So they'd shift the counter and start counting from 1 this time. Some people do that. I'm not saying that I want you to do this. I'm saying some people do it. You can't be confused when you see it. So they want to make the power be n like so, you know. And if you note now, if I'm saying that the power is n, you can see that the thing multiplying x is still always negative, so that's not going to change, but it's 1 more than the power. You see that? You see that this n is 1 more than the power here too. So even though now n is taking different values, you can change it into this. Still, like I said, with negative values. Like so. I don't love it. I would be okay with this format here, but some people are a little pickier in terms of the formatting that they want. Let's discuss the interval of convergence. We knew that this one had interval -1, 1. So radius was 1, which remains the same. What we don't know is whether the radius will now, or the interval will now include -1 and 1. That's something we don't know, generally speaking. Because taking derivatives and integrals, those limits may end up making you either lose or gain those endpoints. But you can clearly see that that's not going to be the case here. I'm going to use, like I said, the boxed version over top, which is my favorite. It's simple enough. If x equals 1, right, this is not going to converge because you're just going to get this, and this diverges by the test for divergence. And then checking the other endpoints, x equals -1, will give us, I'll go back, this also doesn't go to 0. You can see that here, right? This doesn't go to 0 because this thing's going to be alternating between -1 and 1 times n, definitely not going to go to 0. So you can see, for example, that the limit when n goes to 0 of this thing here, taking absolute values to make it clear, it's just the limit of n when n goes to infinity. Oh Lord. There you go. Which is not 0, which is all we wanted. So also diverges by the test for divergence. And so the interval of convergence remains -1, 1. There's no need to include endpoints this time. Okay. So whenever you're solving a problem like this, you do the derivative, the integral that you're supposed to be doing, and then test the two endpoints either way, because you never know what's going to happen. Let me space this out, reorganize this, because I feel like I didn't manage my space super greatly. I'll do one sheet of paper per example. I have 3 more to do with you. Yeah, will this be fine? I think this will be fine. Let's see. Let's see how that goes. All right. Okay, let's go back to doing math here. Our new series is this one. So now I have to be a little bit more creative. Look, remember that what we know is that this thing, we know this. With interval of convergence minus 1, 1. So how can we possibly produce this from this, right? I know that when I take the derivative of the logarithmic function, that it goes, it turns into 1 over x, right? Or 1 over whatever the inside of the logarithm of the logarithmand is. So I'm going to start with taking the derivative of g of x, because I think it's going to make it look close enough to the right-hand side of this black text that I just wrote. So I'm going to start by writing g prime of x as 1 over x plus 1. And now that you know this, it's not so hard to make it look like so. So you can see, let me split the screen in the middle here to manage space, and you can see this is going to be 1 over 1 minus x. You see that? So g prime of x equals the sum, n 0 to infinity, of minus x to the power n. This is a geometric with ratio minus x. R equals negative x here. I just replace the x with the minus x, and you see exactly what's going on. This x gets replaced with a negative x. Right, so I get to write this one more line as you'd be splitting the negative 1 to the power n with the x to the power n, like so. But note, this is not what I want. This is g prime. I don't want g prime. I want g as a power function, as a power series. So I'm going to take the integral. So g of x is the integral of g prime of x, the x, of course, right? The antiderivative of its derivative, yeah? So then g of x will be antiderivative of this whole series. And so we can, of course, by the theorem we read at the beginning, take the antiderivative just on this part. This has no x in here, so only this matters for the antiderivative portion, but I gotta keep the plus c. Usually the plus c goes at the end, but because we're using power series, it's generally more traditional, more common to use the plus c, to write the plus c before the summation symbol, so that you don't think that the plus c is inside of the summation. So you don't keep adding plus c, plus c, plus c, plus c, making the series diverge. So you would just do the plus c on the outside before the summation here. That's most common. So I would do add 1 to the power, divide by the new power, and from 0 to infinity, like so. Again, some people will be bothered by this power not being n. They'd want you to sort of shift this. And so when n equals 0, you start with a 1 and the exponent. So a lot of people would make this start at 1. So again, right, you want the power of the negative 1 to start at 0, but because n is 1, you can't put n there because that would make it start at 1. You have to make n minus 1, because now when n equals 1 on this second series, you get negative 1 to the power 0. When n equals 0 on this series, you get negative 1 to the power 0, saying that they start at the same value, and then you would get this. Either of the two are acceptable. I'm okay with the first format, but you gotta really know whether the person you're taking this class with is pickier than I am with these. Okay. This sort of shift in summation symbol is kind of an interesting skill to develop as well. It's kind of a trade-off. You subtract 1 from every single n inside of the summation, and in exchange you add n here, in the bounds for the summation. Okay, but I'll use the boxed one, which is the first one that we got. And you can see that the plus c is kind of bothersome to have. So I'm going to use this plus to get rid of this plus c in the way that we usually do. I'll just plug in, again, go back. Was it g ln of x plus 1? So we know that ln of x plus 1 equals this. In the interval at the very least, this interval, negative x needs to be between negative 1 and 1, which is just making x be between negative 1 and 1. It's all the same. So maybe if I plug in x equal to 0, right, then I should be able to find out what c is. I'm going to pick something within this interval, and I'll choose x equal to 0 to write this new equation and say that's the natural log of 1 equals c plus the summation. Okay, from n equals 0 to infinity. Gotta be careful with those zeros to the power of zeros here. So I'm gonna be slightly careful, but that doesn't matter here. It's never gonna happen because the lowest power that shows up is 0 plus 1. So it's 0 to the power 1. All of this is going to be 0. So just adding a bunch of zeros here. So c is the natural log of 1, which is 0. So c equals 0. And so we can finally write that our summation is x plus 1 equals minus 1 to the power n minus 1 by dropping. Sorry, I said I was going to use the boxed version there, right? And from 0 to infinity, minus 1 to the power n, x to the power n plus 1, all of that over n plus 1. So I'm going to box this. This is, I want you to be able to do this on your tests, but also this is a common power series to use. And so this also is a series that most students in Calculus 3 need to have memorized, okay? Think of this as going back to Calculus 1 and having to have memorized the derivative of the logarithm or the derivative of the arctangent or something. This is kind of important to have memorized. No, we're not done. We found the series, but if you go back to the statement of the problem, we still need to find its interval of convergence. You see that? Before, we knew that the interval of convergence was this one. And when we made the sort of the calculus and algebraic changes, we got that this at the very least was the new interval. The radius remains the same. So x still needs to be in the same radius from 0. But we may end up having to include the endpoints, like I said. Depends on the function case by case. So we have to test. So let me go ahead and check the two endpoints. So I'm going to check x equals 1. To when x equals 1, this is telling me, and look how funny this is. This is pretty cool. Plugging in x equals 1 just gives me, on the right-hand side, the summation, minus 1 to the power n over n plus 1, and 1 to a certain power, which is always equal 1. So it's not going to make a difference. And I just end up with this. if you stare at this for long enough, this is an alternating series with your Bn being Bn equals 1 over n plus 1, which is decreasing, positive, its limit is 0 when n goes to infinity. So this means that this thing converges by the alternating series test. Which is awesome. If you stop to think about it for a second, this means that we now get to include this side of the interval. So the interval of convergence includes x equal to 1. I think this is pretty cool. Okay. X equals to 1 makes the series converge. So we're going to include that in the interval of convergence. And now let me go ahead and check x equals -1 to see if I also include the left side. N equals 0 to infinity of -1 to the power n over n plus 1 and -1 to the power n plus 1. I'm plugging that into this blue series. X is -1 right here. This is what I'm doing, okay? The series that we got, which was part 1. Now we're trying to find its new interval of convergence. And now if you rearrange this a little bit, you can write this like so. All right, this is decomposing these powers here into 3. And you end up with this. I think I'm going a little slower than I'd like on this video, but I think this is sort of crucial idea. So it's kind of worth it that we spend a little longer. And this, you see, this is -1 to an even power. I added the 2 powers here to get a 2n. -1 to an even power is always positive. Isn't that crazy? This is always positive. So by plugging in -1, you would expect some alternation, but there was already alternation to begin with. So there's alternation here, the 2 alternations sort of cancel each other out, and you end up with no alternation whatsoever. This is completely positive all the time, and then this is negative, so the whole series remains negative all the time. I can bring a -1 out of the series because I know it converges, or, well, it doesn't converge, but I know the limit is going to be one thing, so the right-hand side here will not converge. If you look at it for a second, you can do a comparison test or a limit comparison test with the harmonic series, right? This is, if you want to look at it like so, look. If I open big parentheses, when n equals 0, this is 1. When n equals 1, this is 1/2. When n equals 2, this is 1/3. And so on. So this, again, shifting, starting at 1 now. This is exactly the harmonic series, which diverges because it's harmonic. So what does that mean? Let's pause here for a second, see if you get what I just did. Let me go back a second and then conclude that because the series diverges when x is -1, but converges when x is 1, then if I go and copy this, I can see that the conclusion of the problem, don't remember how to paste. Is it with the finger here, with the hand? Maybe gotta be with the pen. Okay, don't remember. And we'll just write it again then. So that means we have this series n equals 0 to infinity, minus 1 to the power n, x to the power n plus 1 over n plus 1 equals L natural log of x plus 1 with interval of convergence -1, 1 closed. And so this is the end of this problem. But I want to tell you one cool application about this, which I think is bonkers, completely bonkers. Because we know that the natural log, the x equals 1 is included in my interval of convergence, I might as well, if I want, plug in x equals 1 again into this whole equation to see that the sum, n equals 0 to infinity, equals the natural log of 2. Yeah? And if you, again, take a little longer, do the shift in the ends that we talked about before, only on the left, there's no change that needs to happen. So you add 1 to the limits of the summation, and that allows you to subtract 1 to every n that appears in the summation. So subtracting 1 from this gives you just a regular n. Subtracting 1 from this gives you a regular n minus 1, and that's the natural log of 2. This is one of the ways to show that the alternating harmonic series adds to the natural log of 2. So we know that the alternating harmonic adds to the natural log of 2 here. So that's, I guess, observation number 1. We know the summation, right? And the observation number 2 is you don't know the natural log of 2. If you think about it, you only get it from a calculator. And if you ask yourself, how does the calculator do it, right? Again, the calculator looks at this, or the person who programmed the calculator knows this equation that I just boxed. So whenever somebody goes and wants natural log of 2 with a bunch of decimal places of precision, they instead use this summation. So they can say that this is approximately, plug in n equals 1 to get 1 over 1. I plug n equals 1 in here. So I'll do it step by step. I'll do this. 1 minus 1 over 1 plus -1. 2 minus 1, plug in n equals 2 over 2. Plug in n equals 3 over 3. Plug in n equals 4. Subtracted the wrong thing there. So maybe I'll stop at 4. And of course I could add more if I wanted. But the calculator will add as many of those terms as it needs, as it wants, as the user needs. We're going to discuss this. But the first one, this gives -1 to the power 0. So all of this is 1. This gives -1. So -1/2. Plus, this gives you positive again. So it's alternating, as you know. So if you add this, we go ahead and try to maybe find a common denominator for all this. So we can do, what can we do here? Do a 12. Let's multiply everything by 12 over 12 like this. So we get a 12 over 12 for the 1 minus a 6 over 12. I'm not really multiplying by 12 over 12, right? I'm just using 12 as the common denominator. So this one goes 6 over 6. And this one goes 4 over 4 to give me a 4 over 12. Positive and minus, and this goes by 3 over 3 to give me a 3 over 12. So it's 12 minus 6 plus 4 minus 3, all of that over 12. Right? Hope you're following what I'm doing. It's a 16. If I get the positives together, minus 9 over 12. Right? So that will be a Am I right about this? I think so. 7 over 12, I think. Seven over 12. And what we got was an approximation for the natural log of 2. So if I go on my calculator right now, let me go ahead and open it just to finish this point strong. I want this point to make sense to you. If I calculate the natural log of 2 directly on my calculator, the left side will be the natural log of 2 with my calculator would be 0.6931 more or less. And if I calculate this side, 7 over 12, I will get 0.585833. So it's kind of far away, but what happens is that you get closer and closer. For example, if I add the next term, so you see that this is 1, 1/2, 1/3, 1/4. If I now add plus 1/5, right? Plus 1/5, as you know, is 0.2. If I add 0.2 here, I get to 0.7833. So we were undershooting before because the answer is closer to 0.7, but now would be overshooting. But we're closer, right? We were about 0.12 away, right? Just about 0.11. Now we're under 0.8 away of the answer. So just add more and more and more until you're happy with how close you are. And we're going to talk about estimating how far away you are later on. This video is getting kind of long, so I'm going to stop this point here. But I think this is a pretty cool idea, pretty interesting application. Like I said, how does the calculator even know to give you this answer? Well, like this. It does this until it's satisfied with how many decimal places the calculator can display. Also note that this is not necessarily true only for the natural log of 2. Any x that you want to use in here, if you want to find the natural log of 1.5, go back, choose x equals 0.5 here, and then I do the same. Let me stop for a second and just do these two examples a little more quickly. Taking longer than I wanted this to take. But this one has a similar idea, so I'm going to take the derivative of h. The arctangent has derivative equals this, which means that h prime of x is 1 over 1 minus x squared, which will be the summation of minus x squared to the power n equals 0 to infinity. So minus 1 to the power n, x to the power 2n, like so. So now this is the derivative of h, but I don't want the derivative of h, I want h. So I got to take the antiderivative. So I use the reverse power rule, add 1 to the power. Everything else remains the same. Add 1 to the power, divide by that new power, and keep the summation happening between 0 and infinity. And again, I plug in 0 to find c. You can see that this is always going to be 0. So the arctangent of 0, because this is h, is c. So the angle whose tangent equals 0 is 0, c equals 0. So that means that we had arctangents of x is the summation n equals 0 to infinity of minus 1 to the power n 2n plus 1 x to the power 2n plus 1. This is the series that I'll box. This is a power series representation for the arctangent, for the tangent inverse of x. Again, I think we already calculated this in a previous video, minus x is the ratio of the power series. So this would have radius whenever minus x squared actually, right? Let me double check what I did here. I think I made a mistake here. Let me fix this. This is minus x squared like so, with the squared and the negative together. Kind of knew what the answer was supposed to be, and I skipped some of the steps. Yeah, the rest should be correct though after this. Like this. This is your ratio. And now we needed this to be less than 1, or between -1 and 1, which is just x between -1 and 1. We did this math in the previous video. So this has radius. The radius remains the same after taking derivatives and integrals. So the radius here is still 1, but then again we have to check the two limits of integration. The two endpoints of the interval. So we need to check what happens when x equals 1. Let me take this away a little further down. I'm almost done with this video. It's getting really long now. X equals 1 gives you n 0 to infinity minus 1 to the power n x to the power, so x is going to be 1, so it's not going to make a difference. If you take Bn equals 1 over 2n plus 1 like so, again the alternating series test. I'll let you do the work of verifying the conditions of this, but your Bn, the limit equals 0, and it's also decreasing. It's pretty obvious. So by the alternating series test, this converges. So taking the integral made it converge at the endpoint of 1. Now I gotta also check the other endpoint, x equals -1. And we gotta see, again, my expectation will be that it will diverge, but I have to go and check, right? I never know. Never know. I never know. And so, gotta check mathematically. Look at how crazy this is now. Before, what happened was that by rearranging the powers, you always got some odd power, right? Or I think you always got some even power before, and so the -1 didn't happen. Now look at this. This is always odd. This is always odd. The power here, 2n plus 1 is always odd because we're talking integers. So this is always going to equal -1. There's no alternation happening in this circled part, but there is alternation happening here. So this means I have a -1 that's staying still, and a -1 to the power n that's alternating. So this is also alternating. Maybe if I bring the -1 out, you can see. I wouldn't want to do that actually. I'd leave everything inside of the summation and maybe do this. There is alternation happening, you see? So this is also an alternating series with the same Bn. And it also converges. And so this will be closed at -1 as well. So what can we really say? In the end, we can say, to close this example, we can say that the arctangent of x equals the summation n equals 0 to infinity minus 1 to the power n 2n plus 1 x to the power 2n plus 1 with interval of convergence closed -1, closed 1. Completely bonkers again. like I said, we gained 2 endpoints. And I'm too excited about this, which is why I think this video is taking too long, because this is really one of the coolest things that you can do with power series. One of them. And there's a famous formula that you can do here, that you can deduce here whenever you plug in x equals to 1. Because now that we know it is one of the endpoints for integration, we can do this cool formula here, and I'm going to show you what's going on. So I'm just double checking one thing here for a second. And whenever you plug in x equals 1 here, now on both sides of this equation that I just wrote in blue, you get that the arctangent of 1 equals the summation minus 1 to the power n to n plus 1. You see, this is not changing at all, because this is 1 to the power whatever. It's remaining 1, so you get this. But what's the arctangent of 1? Let's stop for a second and think about it. What's an angle that you know whose tangent equals 1? Yeah, in the range of the arctangent function, right? So if you stop to think about it, this is pi over 4. 45 degrees. So now, all of a sudden, there's a pi going on. If you take this 4, multiply over, you get that pi equals n equals 4 to infinity, equals 0 to infinity 4, negative 1 n to n to the power 2n plus 1. And all of a sudden, if you need to find approximations for pi, well, then there you go. You got this series here. Pi is going to be approximately, and you can add as many of these as you'd like. Plug in n equals 0 in here. You see, this is 1. This is 1. So you get 4. Great start. Yeah, you know, pi isn't 4, but it's close enough to 4, right? The next term, when plug in n equals 1 now, plug in n equals 1, you're going to get 4 negative, because it's negative 1 to the power 1. And this is 2 plus 1, 3. Right? 4 minus 4 thirds. And you can see now you're undershooting, because you're above 3.14, 4. Now you subtract more than 1, 4 thirds. Under 3.14, under 3 actually. But you're off by less now. Now you should add 4. Now n equals 2 would give you a, will that be 4 plus 1, 5? And then maybe I'll do one more. It will be negative 4 over, what's that at this point? N equals 3 to get 6 over 7. So you can see the bottoms are going to be the odd numbers. This series is because of the 2n plus 1, right? This is going to be just the odd numbers here at the bottoms. And the series is going to be alternating, and you're going to get all 4s at the top, just alternating. So 4 over 9 and so on. I'm going to stop here to get this approximation, and I'll use my calculator on the right side of this to really, like I said, drive this point home and get 4 minus 4 thirds plus 4 over 5 minus 4 over 7 plus 4 over 9. And I get approximately on the right side, this right side is approximately as well, 3.3397 more or less. And again, pretty far off, but a lot closer than we began at 4. And if you need more accuracy, just keep adding more and more terms of the series. So this is known as Leibniz formula for pi. So important. And it is how most modern calculators nowadays get approximations for pi. It's pretty systematic. It's great for machines, for computers to use to find pi. I don't know if you've ever thought about it. Where does pi even come from, right? How do you even know what pi equals? What's the next digit of pi? You know, how do people know? How do mathematicians know? So I'm going to use this last example here to stop, to end this video finally. And I hope this is going to not be too long and you're going to be able to watch it. So since you know that you can take integrals of power series, if you have a complicated function to take the antiderivative of, you see this would be a difficult integral to solve. You have this 1 plus x to the power 7. You have to do a u sub and then 0.5 plugged in. It wouldn't be horrible, but it would be a little complicated. And again, we're going to handle variations of this. But with series, that becomes very, very straightforward in the sense that as long as you are okay with an approximation rather than the exact answer. So let me just do this real quick. I know that 1 over 1 plus x to the power 7 is 1 over 1 minus x to the power 7, like so, which equals, if I use my geometric series now, the summation, and from 0 to infinity of minus x to the power 7 to the power n, and that will be n equals 0 to infinity by splitting the negative 1 to the power n with x to the power 7n. Yeah. Then I should be fine here. So by taking this integral, I can just take the integral of the series instead. So term by term, I'm going to integrate. Rather than do all of this again, let me integrate. I know how to integrate this. This is just a regular polynomial, so I keep the summation. Add 1 to the power, divide by the power. I've solved my integral. I'd add the plus c if that were an indefinite integral, but because this is definite, I just evaluate that from 0 to 0.5. Yeah. Okay. When I plug in, I go back down here. When I plug in 0.5, I'm going to plug in 1/2 instead, because 1/2 and 0.5 are the same thing, as you know. I get 7n plus 1 over 7n plus 1. But then when I plug in 0, I just got a bunch of zeros. Every time here, 0 plus 0 plus 0 plus 0. So I get this. So I only care about this series, really. And if I go back, the problem says I get to use the first 3 terms. So I only need n equals 0 to 3, to 2, I guess. 0, 1, and 2 give me 3 terms. So I'm going to use an approximation now, no longer equal. In this fraction, I get to rewrite like 2 to the power 7n plus 1, 7n plus 1, like that. So when I plug in 0, so I only have 3 terms now. So I'm doing this. Plug in 0, I get 1 over 2. That's easy enough. And then minus, because n equals 1 now. N equals 1 gives this an 8, makes it an 8. And this is another 8. Now, n equals 2 gives me 14, 15, and then times 15. So, of course, you can use a calculator to estimate this, but this is what you have. Now, no, this is pretty close to the answer it needs to be, because the next term is only going to make this change by very little. 2 to the power 15 already is what I have. So this is already so small that these two already probably give me a good approximation. And even this, 2 to the power 8 over times 8, the 1 divided by that is already so small. So probably 1/2 is already a great approximation. So again, with a calculator, this is not too hard to estimate. Or even if I'm happy with a fraction, I don't need a calculator. I can just find common denominators and see that as a fraction. So it's a pretty cool application, I think. I'm going to stop the video right now because it's already way longer than what I wanted. Feel free to rewatch this as many times as you need. Understand the key ideas, which are all the same, and also the super interesting conclusions that we reached here.